Learners, welcome to this session. I am your lead instructor for today's technical deep dive.
And I'm here to provide the detailed analysis.
We are shifting gears a bit today. We're moving from general knowledge to specific doctrinal revision. The tone will be professional, calm, and strictly focused on the syllabus.
That's right.
If you're listening to this, your objective should be very clear. A complete, structured revision of ammunition, grenades, and mines.
Precisely. We are here to ensure that when you face an examination or perhaps an inspection, you're not just reciting definitions from a book.
No, absolutely not.
Our primary goal today is really to move beyond that rote memorization. We need you to understand the mechanical and tactical why behind all this hardware.
The underlying principles.
Exactly. If you understand the physics of, say, a gas seal, you won't forget the composition of a cartridge case. It just makes sense.
Or if you understand the tactical need for surprise, then the whole design philosophy of modern artillery systems becomes much clearer.
It falls into place.
Exactly. So to do this, we're going to build this revision session through 4 distinct conceptual layers. This should help with your mental mapping of the subject.
A clear roadmap.
First, we will tackle small arms ammunition, what we call SAA. We'll cover its construction, the internal ballistics, and of course the evolution of caliber.
Then from there, we'll scale up. Layer 2 will be artillery and mortars.
Yeah.
We'll examine the concept of the complete round, the accuracy systems that are so critical, and the terminal effects.
And layer 3.
Layer 3 is area denial. This is where we get into the doctrine of mine warfare, how we calculate stopping power, and of course, grenades.
Okay, and to wrap it all up.
Finally, we'll conclude with layer 4, future technologies. This is where we look at what's coming next. Range enhancement, smart munitions, and guided systems like the Excalibur and the Krasnopol.
Excellent. Let's begin immediately then. Layer 1, small arms ammunition, SAA. Learners, we have to start with definitions and scope. It's the foundation.
It always is.
So generally when we speak of SAA, what are we referring to? We're talking about ammunition fired from weapons normally used by the infantry. Caliber-wise, there's a limit generally accepted up to, what, 1 inch?
1 inch is the common cutoff, yes. And we must contrast this immediately with artillery. It's a different beast entirely.
So define artillery for us.
The term artillery covers any non-personal offensive weapon where gas pressure, which is derived from the combustion of a propellant charge, is used to eject a missile.
The key distinctions there being non-personal and the scale of the mechanics involved.
Absolutely. But for now, let's keep the focus on the round in your hand, on SAA.
To master SAA, you must be able to deconstruct the round into its 5 essential components. This is non-negotiable.
And it doesn't matter if it's a 5.56 millimeter or a larger caliber, the architecture is fundamentally consistent.
So what are the 5?
You have the bullet, the cartridge case, the propelling charge, the firing system, and the cap.
Let's break those down. We'll start with the bullet.
Yeah.
And a key point here is that it is not just a solid piece of metal.
Not at all. A modern bullet consists of 2 primary parts. You've got the core and the envelope.
The core is 4.
What purpose?
The core provides the density. That's where the mass comes from, which is required for momentum and penetration. In a standard ball round, this core is lead.
But not always.
Right. For armor-piercing or AP rounds, that lead core is replaced with one made of hardened steel. Much tougher.
And this core is encased in the envelope.
Correct. Usually made of cupro-nickel or something called gilding metal.
And the purpose of that envelope is critical, isn't it? It has a very specific job to do.
It's a balancing act. It must be tough enough to engage the rifling of the barrel without stripping, which would cause a loss of spin and accuracy. But at the same time, it has to be soft enough that it doesn't cause excessive wear to the bore itself.
And in terms of design, we're looking at a cylindrical body with an ogival nose.
Yes, ogival just means a pointed, curved nose. The base may be square, or it might be boat-tailed to improve the aerodynamics and stability in flight. Now here is a crucial exam point, something that often trips people up. SAA bullets do not have driving bands.
That is a critical distinction. Driving bands are a feature exclusive to artillery, and we will absolutely be discussing them later. But for SAA, you will not find them.
Okay, let's move to the second component, the cartridge case. You've called this the powerhouse of the round.
I think that's fair. It's generally made from a specific material, cartridge brass. Learners, you should take note of the specific composition here. It is 70% copper and 30% zinc.
And that very specific alloy, that 70-30 mix, it isn't chosen at random, is it? There's a deep mechanical reason for it.
It all comes down to the mechanics of obturation.
Obturation, define that for us.
Obturation is, simply put, gas sealing. The case has to be a waterproof container for the propellant, yes, but its primary function during the moment of firing is to act as a gas seal.
How does it do that?
Well, when the propellant ignites, the pressure inside the chamber skyrockets. The brass case needs to expand instantly to press outwards and grip the chamber walls. This seals the high-pressure gas behind the bullet, ensuring it all goes into pushing the projectile forward.
But it can't just expand. It also has to come back.
That's the other half of the magic. It has to be elastic enough to retract, to shrink back slightly after the pressure drops. This allows the extractor to pull the spent case out of the chamber.
And if you used a different metal?
If the metal were too hard, say like steel, it wouldn't expand enough to seal properly. You'd get gas leakage. If it were not too soft, it would expand, but then it would stick in the chamber, or even rupture.
A catastrophic failure.
A very serious one. So that 70-30 brass alloy offers that perfect balance of expansion for sealing and retraction for extraction.
Okay, that makes sense. That brings us to the firing system and the cap.
In our service cartridges, if you look at the base of the case, you'll find a cap chamber. This is connected to the interior, where the propellant is, by two small fire holes.
And the cap itself.
The cap is a soft metal cup, and inside it is an igniferous initiating composition, a tiny bit of very sensitive explosive.
The mechanism here relies on the anvil. What is that?
The anvil isn't a separate part. It's actually formed into the center of the cap chamber itself. It's a small, hard point.
So the sequence is firing pin strikes the cap.
It crushes that sensitive composition against the anvil. That sudden crushing force, that friction and heat, is enough to detonate the composition.
And that detonation sends a flash to the fire holes.
A very hot, intense flash, which in turn ignites the main propelling charge, which is usually NC powder or cordite, and that's when the real power is unleashed.
Now that we have the components, let's trace the sequence of action. This is internal ballistics, what happens inside the gun in that fraction of a second. We can break this into 4 steps for revision. Step 1 is simply loading.
Right. At this stage, the round is chambered. The bullet moves forward to just engage the commencement of the rifling. The cartridge case is sitting snugly in the chamber, and crucially, the base of the case is fully supported by the bolt or the breech block.
Then comes step 2, ignition.
The cap detonates, as we just described, the propellant ignites, and gas pressure begins to rise incredibly rapidly. This leads immediately to step 3.
Which is obturation by the case.
Exactly what we discussed regarding the brass alloy. The immense pressure forces the walls of the case hard against the chamber. The upper portion of the case, which is a bit thinner and softer, presses especially hard.
And the purpose of that is to stop any gas from escaping rearward.
Towards the fire. It's a fundamental safety and efficiency mechanism. All the energy has to go in one direction.
You mentioned there's a critical failure point here that we need to remember for exams.
Yes, headspace. You have to understand headspace. This is the small gap between the base of the cartridge case and the face of the bolt.
If that gap is too large.
If there's excessive headspace, the case isn't properly supported from behind. When it fires, the pressure will stretch the brass backwards to fill that gap. This can cause it to fracture or even separate completely.
A case head separation.
A very dangerous malfunction. Similarly, if a chamber is badly worn or scoured from long use, the case will expand beyond its elastic limit into those imperfections.
And it will retract properly.
It will get stuck. This leads to a separated case during extraction where the head of the case is ripped off, leaving the body behind. That's a stoppage that renders the weapon useless in a firefight until it's cleared, which is not a quick process.
Okay. Step 4 is the bullet setup. It's also known as the upset. This is a concept that often catches learners off guard. Can you explain what happens to a standard ball bullet the instant that pressure hits it?
It's a fascinating bit of physics. You have to think of the solid metal behaving, for an instant, like a fluid. When that sudden, massive pressure wave hits the lead core at the base of the bullet. And because the nose of the bullet is being held back by its own inertia and by the friction of the barrel, the base of the bullet actually mushrooms. It bulges outward. This is called setup.
So it physically gets wider at the base, and this mushrooming serves a purpose.
It serves 2 absolutely vital purposes. First, that bulge presses the soft envelope material into the rifling grooves of the barrel, creating a perfect forward gas seal. No gas can leak past the bullet.
And the second purpose?
It ensures that the rifling gets a deep, positive bite on the bullet. It engraves the bullet, which is what imparts the spin that stabilizes it in flight.
However, you've mentioned there is a major exception to this rule. A type of round that does not set up.
Correct. the armor-piercing, or AP round.
And why not?
Because AP rounds have that hardened steel core, they're simply too hard to mushroom or set up under pressure. They would shatter before they deformed in that way.
So they must rely on a different mechanism to achieve that gas seal and engage the rifling.
They do. They are manufactured to a very precise and slightly larger diameter. They're designed to bottom out in the grooves of the barrel simply by their size. They barricade the gas by sheer fit and strength rather than by deformation like a ball round.
An excellent distinction to remember. Okay, before we leave SAA, we must cover the evolution of caliber. We've seen a significant doctrinal shift from 7.62 millimeters to 5.56 millimeter.
Yes, and this was driven entirely by data, by combat analysis. Specifically, analysis of conflicts post-World War II showed that a staggering 85% of infantry engagements occur within 400 meters.
And the 7.62 millimeter round was designed for what range?
The 7.62 millimeter was designed for effective engagement out to 800, even 1,000 meters. It was, in essence, over-engineered. It was too powerful for the realistic role of the standard infantry rifleman.
So the move to 5.56 millimeter was really about efficiency.
Efficiency, logistics, and combat effectiveness. The 5.56 millimeter round is lighter, which means a soldier can carry more ammunition for the same weight. That's a huge logistical benefit.
And it produces less recoil.
Far less recoil. This improves accuracy, especially for soldiers under stress in rapid-fire situations. It allows for faster, more accurate follow-up shots.
And then there's the concept of wound ballistics. This is key.
This is a very important doctrinal point. In modern warfare, incapacitating an enemy is often tactically superior to killing them outright.
Why is that?
A single casualty who is incapacitated drains enemy logistics. They require evacuation, medical treatment, administration, and they take other soldiers out of the fight to help them. The 5.56 millimeters is designed to tumble upon impact, transferring its energy in a way that maximizes this incapacitation effect.
Learners, these are numbers to remember. The lethality thresholds. It takes approximately 407 joules of energy to defeat standard body armor.
But it only takes about 81 joules to incapacitate a human target.
So that 81 joule figure is your baseline for effectiveness.
Yeah, it is.
Okay. Having mastered the personal weapon, we now need to scale up to the heavy systems. We're transitioning from the direct fire of the rifle to the complex, indirect fire of artillery. This is layer 2.
A whole new world. In artillery, we deal with what's called the complete round.
That consists of 2 main parts.
The projectile, which is the missile itself, and the cartridge, which provides the motive power. The anatomy of the projectile is much more complex than what we saw with SAA.
Let's start with the most critical difference. We mentioned it before. The driving band.
Absolutely. Remember, we stressed that SAA bullets have no driving bands. Artillery shells must have them.
Explain its function.
A driving band is a soft metal ring, usually copper, fitted near the base of the shell. Because the main steel body of the shell is too hard to be forced into the rifling, this soft band is what actually engages with the rifling.
So it serves the same 2 purposes as the upset in an SAA bullet.
Precisely. It provides the spin for stability, and it creates the all-important gas seal behind the projectile.
What are the other landmarks on a shell that we should know?
You have the ogive, which is the pointed nose section. You have the main body and the base. On longer, more modern shells, you'll also find the borlet.
The burl.
It's a narrow, smooth machine surface near the front of the shell body. It's designed to ride along the top of the rifling lands, helping to center the shell in the bore and keep it stable as it travels down the barrel.
But perhaps the most sophisticated component of the modern shell is the fuse.
You can think of the fuse as the brain of the shell. Its job is to initiate the explosive train at exactly the right time and place to achieve the desired effect.
And you must know the 3 main types.
First, you have simple impact fuses. They are triggered by physical contact with the target. Second, you have altitude fuses.
How do they work?
They use either a barometric pressure sensor or a small radio altimeter to measure their height above the ground. They are set to burst at a predetermined altitude for an airburst effect.
And the 3rd type, the one that really revolutionized artillery lethality.
The proximity fuse, or VT fuse. This uses a miniature radar transmitter and receiver. It actively sends out a signal and detonates when it detects the reflection from a target nearby.
It doesn't need to hit, it just needs to be close.
And that is devastating against aircraft or troops who think they are safe in trenches. There are also passive versions that use infrared sensors.
But with these smart fuses comes the critical need for safety and arming devices.
You absolutely cannot have a fuse arming itself inside the barrel or near the gun crew. That would be catastrophic.
So how do they prevent that?
Fuses have internal mechanisms that must detect that they have traveled a safe distance from the gun before the firing train is aligned. This is usually done by sensing the high acceleration of firing, followed by the sustained spin of the projectile. It's a sequence of events that can only happen after firing.
They also incorporate self-destruct mechanisms.
Yes, to prevent the battlefield from being littered with unexploded ordnance if they miss the target. It's a critical feature.
Let's look at the power source, the cartridge. In artillery, we distinguish between two main systems, breech loading, or BL, and quick firing, or QF.
This classification is based on how they achieve obturation, that gas seal we keep coming back to.
Let's start with breech loading, BL.
BL systems are typically found on heavier, often older, equipment like large naval guns or heavy howitzers. The propellant isn't in a brass case, it's contained in separate cloth bags.
So you load the shell first, then the bags of propellant.
Correct. You load the shell, then one or more bags depending on the range required. Ignition comes from a separate tube that's inserted into the breech block.
So where does the gas seal come from?
The crucial point is that the gas seal is provided by the breech mechanism itself, a special pad on the breech block, not a metal case.
Now contrast that with quick firing, QF.
QF systems use a metal cartridge case, usually brass, very similar in principle to SAA, but much, much larger. The case itself expands to seal the gas in the chamber.
And the advantage is speed.
It allows for much faster loading cycles because the propellant and primer are all one unit, hence the name quick firing. These are standard in most modern high rate of fire systems.
Now, artillery is completely useless if it misses the target. So we must discuss accurate engagement of targets by indirect fire. And indirect fire means you cannot see the target from the gun position.
And this introduces a host of variables or non-standard conditions. You have weather, wind at different altitudes, changes in air density, even tiny errors in the gun's location or the rotation of the Earth. All of these have to be accounted for.
So to achieve accuracy, the armed forces employ a suite of technological solutions.
A system of systems.
Let's list the key systems you need to recall for an exam. For the gun's own location, we use what?
The PADI-S Mark III. That's the position and azimuth determining system. It's an inertial navigation unit that tells the battery its exact grid coordinate and orientation on the map to within a few meters.
Okay. For target acquisition,
We use high-powered optics, laser rangefinders, and high-precision theodolites to get an exact location for the target.
what about the weather, which is a major variable?
For that, we use the microcora or digicora meteorological systems. These send a probe up into the atmosphere on a balloon.
And it radios back data.
Exactly. It sends back real-time data on wind speed, direction, temperature, and air density at various altitudes. This MET message is fed directly into the ballistic computer.
And finally, the gun itself is a variable. As a barrel wears out, the muzzle velocity drops. How do we compensate for that, shot by shot?
With a muzzle velocity radar, specifically the DR-810 system. This is a small Doppler radar mounted on the gun that measures the exact speed of the shell as it leaves the barrel.
And the ballistic computer uses that data.
Instantly. It adjusts the calculations for the very next round based on the actual performance of the last one. It's a constant feedback loop.
All of this incredible technology serves one primary doctrine. First, salvo effectiveness, FSE.
FSE is the holy grail of modern artillery. Combat studies have proven time and time again that the maximum number of casualties occur in the initial burst of fire.
Before the enemy can react.
Exactly. Once shells start landing, the enemy takes cover. Therefore, the old method of firing a shot, seeing where it lands, and then adjusting is obsolete. We cannot walk the rounds onto the target. We must hit the target with the very first salvo.
And achieving FSE requires both speed and computation.
It requires guns with an extremely high rate of fire, like the 155mm FH-77 Bofors, which can fire 3 rounds in just 14 seconds. You combine that with ballistic computers that process all that data from PAID, microcora, and the DR-810 instantly.
The result is a surprise, lethal burst on target.
Before the enemy even knows they're being engaged. That is FSE.
Before we leave this layer, we do need to touch on mortars and rockets. How do mortars differ from guns?
The main distinction is that mortars are usually smooth bore. They have no rifling. This means the projectile cannot rely on spin for stability in flight.
So how are they stabilized?
Mortar bombs are fin stabilized. They look like streamlined darts with a large tail unit fitted with fins.
And their propulsion system is modular, which is different from the standard QF round.
Yes. In the tail unit, you have a primary cartridge. That gives it its minimum range. To increase the range, you clip on additional secondary or augmenting cartridges.
These are often horseshoe-shaped.
Correct. They are horseshoe-shaped charges that fit around the tail boom. The more charges you add, the farther it goes.
Okay, what about rockets? Like the 122 millimeter used in the Grad system. They have a very unique way of adjusting their range.
They do. A rocket motor burns for a set time, producing a set amount of thrust. So to shorten the range, you can't just use less fuel. Instead, you have to intentionally add drag.
Ow.
They use brake rings. These are metal rings that are clipped onto the nose of the rocket. A small brake ring creates some drag and reduces the max range of 20 kilometers down to roughly 16. A large brake ring adds even more drag, cutting it down to about 12 kilometers.
That sounds crude.
It is crude, but it is a simple and effective method of range control for that type of system.
All right. We have covered how we deliver the payload.
Yeah.
Now we must examine what happens when that payload arrives. This takes us to layer 3, terminal effects and area denial.
Terminal effect is all about the conversion of the shell's potential and kinetic energy into destructive work on the target. Learners, you should memorize the 5 damage types.
Let's list them.
First, pressure from the blast wave. Second, splinter or fragmentation. Third, shock, which is the direct impact energy. Fourth, concussion, the atmospheric overpressure effect. And fifth, psychological fit, the sheer terror effect of being under bombardment.
This leads us directly to mine warfare. The goal here is not just killing. It is about creating something called stopping power.
Stopping power is a cumulative tactical effect. We lay minefields with 4 specific aims in mind. You need to know these.
What are they?
First, to delay the enemy's advance. Second, to disorganize their attack formation. Third, to restrict their maneuver, forcing them into pre-planned killing zones for other weapons. And finally, attrition causing casualties and equipment losses.
You mentioned that the key to stopping power is mathematical. It's about density.
Density is the critical variable. It's defined as the number of mines laid per meter of frontage.
And for anti-tank or AT minefields, there's a specific rule of thumb.
The rule of 1 is paramount. A density of 1 mine per meter of frontage is generally considered sufficient to deter a deliberate armored assault. It forces the enemy to either stop and breach it or go around.
What about the characteristics of the mines themselves? Actuation pressures are important.
Very. An effective mine has to be lethal, but it also has to be sensitive enough to be triggered by its intended target and nothing else. An anti-personnel, or AP, mine typically triggers at 8 to 50 kilograms of pressure, the weight of a person's footstep.
Whereas an anti-tank mine
Requires 200 to 250 kilograms. This ensures it won't be set off by infantry walking over it, only by a vehicle.
we must also address international law, specifically Amended Protocol 2.
Yes, this is a key point. Protocol 2 addresses the humanitarian crisis caused by undetectable mines left after conflicts. Modern plastic-cased mines are very hard to find.
So the protocol mandates detectability.
Correct. It mandates that all anti-personnel mines must contain at least 8 grams of metal. This is to ensure they can be found by standard mine detectors during clearance operations. It's a compromise between military utility and humanitarian concerns.
Briefly touching on grenades while we are in this layer.
Grenades are versatile, short-range, hand-delivered missiles. A standard hand grenade has an effective range of approximately 32 meters. Rifle grenades, of course, extend this range significantly.
The key technical point for exams regarding grenades is often about their anti-armor capability.
Yes. An anti-armor grenade doesn't rely on simple blast force. It operates on the hollow charge principle, or the Monroe effect. It focuses the blast energy into a superheated jet of metal that can penetrate thick armor plate.
Okay, so current doctrine is now established. We can conclude our revision by analyzing the future of warfare. This brings us to Layer 4, future technologies and smart systems.
Right, let's start with a fundamental problem, range enhancement. How do we make a standard artillery shell fly further?
There are 4 primary techniques to know. Let's start with the rocket-assisted projectile, or RAP.
The RAP shell has a small, solid-fuel rocket motor in its base. After the shell has reached the top of its trajectory, the motor ignites and provides an extra push.
How much extra range do you get?
It boosts the range by about 25%, but it comes with a downside. The variable burn of the rocket motor makes the shell less accurate. There's a trade-off between range and precision.
Okay, the second method is base bleed.
Base bleed is generally superior for accuracy. It also has a composition at the base of the shell, but it doesn't burn to provide thrust.
So what does it do?
It burns slowly to release gas that fills the vacuum, the area of low pressure that naturally forms behind in the shell in flight. This significantly reduces what we call base drag.
And the range increase.
It increases range by about 15 to 30%, and because it's a much more consistent and gentle process than a rocket motor, it's far more accurate than RAP.
Then we have ERFB and ERSC.
ERFB stands for Extended Range Full Bore. This is purely about improving the aerodynamics. The shell is made longer, more streamlined, with a distinct boat tail shape to reduce overall drag.
And ERSC.
ERSC is Extended Range Subcaliber. This is a more radical approach. It uses a smaller, thinner projectile encased inside a larger, lightweight carrier called a sabot.
Like an APDS round in a tank.
Exactly the same principle.
Yeah.
The sabot fills the barrel but falls away as soon as it exits the muzzle, leaving the small, dense, arrow-like projectile to travel at extremely high velocity towards the target.
Looking beyond the projectiles, at the guns themselves, the future seems to be electric.
We are seeing significant research into electromagnetic, or EM, guns. These use powerful electromagnetic rails to accelerate a projectile instead of chemical propellants. We could see muzzle velocities of 5,000 meters per second.
We're also looking at ramjet shells.
Yes, air-breathing projectiles that could potentially extend the range of a medium gun out to 70 kilometers or more.
But the biggest shift, the most important trend to understand, is the move from mass to precision. In other words, smart munitions.
Absolutely. Let's talk about cargo shells. These are a first step.
They don't explode themselves, they act as a delivery system.
Correct. They are carrier shells. They fly to the target area and then dispense a payload of submunitions. For example, the 155mm Bofors cargo shell carries 72 bomblets. Some are fragmentation for personnel, some are shaped charges for armor.
And we also have RAMs and ATOM.
Yes. RAM stands for Remote Anti-Armor Mine System. It's a shell that delivers small anti-tank mines. ATOM is the anti-personnel version. A single artillery barrage can instantly create a complex minefield deep behind enemy lines.
And then we have the true guided projectiles. Let's talk about the Copperhead and the Krasnopol.
These represent the first generation of truly smart shells. They are laser-guided.
How do they work?
An observer, either on the ground or in the air, must paint the target with a laser designator. The shell has a seeker in its nose that looks for the reflected laser energy and steers itself towards it.
How accurate are they?
Very. The Krasnopol has a stated hit probability of 90% and can target tanks from the top, where their armor is thinnest.
But they have a significant weakness.
Their weakness is weather. Fog, heavy rain, or battlefield smoke can block or diffuse the laser beam, breaking the lock. The observer also needs a clear, continuous line of sight to the target, which puts them at risk.
Which brings us to the next evolution, the M982 Excalibur.
The Excalibur solves the weather and line of sight problem. It doesn't use a laser. It uses a combination of GPS and inertial guidance.
So you just program in a grid coordinate.
Exactly. It flies to a specific coordinate on the map. It works in fog, smoke, rain, day or night. And because it is so incredibly precise,
It allows for close support.
yes, firing within 75 to 150 meters of friendly troops. This was previously unthinkable with heavy artillery due to the risk of error. Excalibur changed the game for supporting troops in contact.
We also have fire and forget sensor fuse munitions, like SADARM and bonus. Can you distinguish between these for the learners?
Both are designed for top attack against armor, but they work slightly differently. SADARM is dispensed over the target area and descends on a parachute. As it comes down, its sensors spin and scan the ground for the heat signature of a tank.
And when it finds one?
It fires a self-forging fragment, an incredibly high-velocity slug of molten metal, straight down through the thin roof armor.
And bonus.
Bonus is similar, but more advanced. It doesn't use a parachute. It uses small aerodynamic fins or wings to control its descent and search pattern. Both are fire and forget. Once they're fired, they hunt for their own targets autonomously.
And this smart technology is even trickling down to small arms with the X-Acto program.
The self-steering bullet.
Okay.
This is a .50 caliber round with a tiny optical sensor in its nose and small internal actuators that adjust steering fins.
How often can it correct its course?
It can make up to 30 course corrections per second. This allows a trained sniper to hit a moving target at 2 kilometers, as the bullet can compensate for wind, weather, and target movement automatically.
Finally, in the realm of aerial delivery, we have smart bombs. We need to know the distinction between the LGB and the JDAM.
It's a very similar story to the artillery shells. The LGB, or laser-guided bomb, is extremely precise. We're talking 3 meters of accuracy. But like the Copperhead, it's vulnerable to weather and requires the pilot or a ground observer to keep the laser on the target.
And the JDAM.
The JDAM, or Joint Direct Attack Munition, is not a bomb. It's a GPS guidance kit that you strap onto a standard dumb bomb. It's the Excalibur of bombs.
It's slaunch and leave.
Exactly.
Yeah.
The pilot gets the coordinates, drops the bomb, and can immediately turn away to escape threats. The bomb flies to its coordinates regardless of the weather. It's the tactical choice for high-threat environments where you can't afford to linger.
Learners, that concludes our 4 layers. We have journeyed from the upset of a 5.56 millimeter bullet all the way to the GPS guidance of the Excalibur shell.
The core theme, the main idea you must take away from this session, is the fundamental shift in doctrine. We have moved away from mass, simply firing volumes of lead in the general direction of the enemy, to precision and efficiency.
It's about achieving the maximum effect with the minimum resources.
Whether it's the calculated stopping power of a minefield or the first salvo effectiveness of a Bofors gun, the goal is always to achieve the desired effect in the shortest possible time with the least amount of waste.
For your exams, I would urge you to focus on the contrasts we highlighted throughout this session. The AP versus ball setup mechanisms, RAP versus base bleed for range enhancement, and the critical limitations of laser guidance versus the advantages of GPS.
And remember, a deep knowledge of the hardware is the absolute foundation of tactical competence. You can't employ it effectively if you don't understand how it works.
Study hard. Dismissed.